Chicago, 1885. On LaSalle Street, a 10-story tower is rising, built almost entirely of iron and steel, weighing barely a third of what a masonry building this size should. According to later accounts, city inspectors briefly halt construction. They believe it may simply come apart, story by story, onto the men working inside it. The architect William Baron Jenney has no torch and no weld available to him. So how do you keep 138 feet of iron and steel from tearing itself apart without fusing a single joint? 14 years earlier, the Great Chicago Fire leveled most of the city. Rebuilt in stone and iron instead of wood, Chicago is now chasing height, but height demands walls thick enough to crush the ground floor in shadow and swallow half the usable space. In older masonry towers nearby, ground floor walls run 4 feet thick just to hold up the stories above them, space that could otherwise be rented as office floor. Jenney's answer is to stop asking the walls to carry the building at all, and let an internal frame do it instead. Hundreds of separate iron and steel members would have to become one rigid structure, and if even one connection in that frame cannot be trusted, the whole argument for building this way collapses. Jenney arrives at this problem already in his 50s. He's a former Union Army engineer who built bridges and fortifications under Sherman during the Civil War. As the often repeated story goes, though it has never been confirmed, he found his answer watching his wife set a heavy book on top of a bird cage and noticing that the thin frame, not the walls, carried the weight. True or not, the anecdote describes exactly what he was about to build. But a frame is only as good as what it stands on. Chicago sits on soft, compressible clay, and Jenney knows that if one footing settles even slightly faster than its neighbours, the rigid iron frame above will tear itself apart from below before a single wall goes up. So before a single column rises, he designs a footing system to spread the load evenly across the site, and by his own account, published soon after completion, this foundation work is the achievement he is proudest of, ahead of the frame above it. The building begins with cast iron columns, hollow, story high, bolted one on top of the next, strong under compression but brittle under tension, supporting wrought iron beams. Onto shelf brackets cast directly into each column, crews set a pair of 12-inch wrought iron floor beams, but erection tolerances mean the bolt holes are cut deliberately oversized, leaving real play in every joint. Left alone, sustained wind load could gradually loosen a poorly secured joint, one small movement at a time. Jenney's fix is a threaded wrought iron rod, bent and hooked into a notch cut in the beam's top flange, then drawn tight by a nut turned from inside the hollow column, cinching the whole joint rigid against the frame. No weld, no fusion of metal into metal, just thread, leverage, and a man's hands reaching into a cast iron cavity to finish the connection blind. Then, partway up the building, the project shifts towards steel. A Pittsburgh mill offers something new, rolled Bessemer steel, cheaper to produce and stronger than iron, still a novelty in American construction. Crews swap it in mid-erection, first for one floor of beams, then for 2 more above it. Every new steel beam has to fit iron already bolted in place, a mismatch, and the floor above sits unevenly for good. The building finishes in a material it did not start in. For the first time at this scale, a skyscraper is standing in part on structural steel. Riveted steel didn't reach this scale until 1889, when Chicago's Tacoma building raised the first fully riveted steel skeleton, and within a decade the practice was standard. Jenney's tower went up 4 years earlier. Rivets already held bridges together by then, but no skyscraper frame had yet been assembled that way. So how do you hold a steel and iron skeleton together before that method exists for a building this size? The skyscrapers of that era, such as Jenney's buildings, were bolted, wedged and clamped tight by hand, cast iron columns joined by threaded rods instead of hammered rivets. Back in 1885, though, bolts and clamps weren't the only thing under scrutiny. The halted inspections from LaSalle Street continue for weeks before officials allow work to resume, and the argument doesn't end there. Decades later, historians would keep disputing what Jenney actually built. His street-facing walls still rest partly on masonry piers, not the iron cage alone, and a committee would later test whether entire floors of masonry could be removed without the structure above collapsing. So was this a true skeleton frame or a hybrid wearing its label? That debate has never fully settled. Whichever verdict history settles on, what actually kept the building standing was simpler than its classification: how well each joint was made. The difference between a connection tightened with care and one rushed to meet a deadline wouldn't show on opening day. It would show after a decade of Chicago wind, after winters of contraction and expansion working every bolt loose or tighter. Exposed iron and steel carried a hidden weakness Chicago already knew well. In a fire, unprotected metal softens and buckles long before masonry fails. Why Jenney's columns were wrapped in fireproof terracotta rather than left bare. Protected this way, his building stood, structurally sound, for 46 years, outlasting nearly everyone who built it and losing its site only to demolition for a larger tower, never to structural failure. What Jenney's frame delivered, more than height, was light. Masonry walls could shrink to a thin, non-load-bearing curtain, and glass could take their place. Clerks and bookkeepers who had spent careers in dim, thick-walled offices now worked beside windows twice the size they'd known. A structural decision about bolts and brackets became a daily, physical experience for thousands of people who never gave the columns a second thought. Architects soon had a name for this new kind of exterior, an early precursor to the curtain wall, hung from the frame rather than holding it up, and a name for the loose circle of Chicago engineers building this way: the Chicago School. Bolted, hand-clamped iron frames didn't remain the standard for long. Riveted steel skeletons replaced them within a decade, faster to erect and far more resistant to loosening under vibration and repeated stress than a bolted joint of the era. Welding itself would not arrive at real structural scale for another 40 years. Even now, steel erectors bolt a frame loosely into place before permanent connections go in. The same logic Jenney's crews used out of necessity, engineers use today by choice. Jenney's tower belonged fully to neither era, not the last iron building, and not quite the first true steel skyscraper either. The home insurance building came down in 1931, cleared for a taller building on the same corner. A plaque set into its replacement calls Jenney the true father of the skyscraper. Long before any torch could fuse a single joint, height depended on a threaded rod, an oversized bolt hole, and one engineer willing to hand-tighten every connection that 138 feet of iron and steel would ever need to hold. These systems shaped the world quietly. If you'd like to see more of them preserved, consider subscribing, and tell us, which forgotten skyscraper should we uncover next?